Greetings, aspiring scientists. Hope you're doing well today. Welcome to my lecture on really 3D molecular shapes, VSEPR theory, maybe a bit of polarity today. We'll see how far we can get while keeping this under 1 hour. So let's go to my slides. We are in 2.2.2 of the IB curriculum on covalent bonding. So first, very short section here on bond order. Important ideas, but really things that we've talked about before, maybe just a little bit of new vocabulary and language surrounding it that we can learn. So, what is bond order? Well, it's essentially the same thing as what we have been labeling single, double, and triple bonds. So, bond order equals 1 is a single bond. Bond order equals 2 is a double bond. Bond order equals 3 is a triple bond. So why write it like this? Well, we need to actually define these types of bonds with a number. And I think the main reason for that is that non-integer numbers of bond order are also possible. You can have 1.5 bonds, 2.3 bonds, 1.75 bonds, these kind of things in between integer numbers, and they can be calculated, which we'll get into, I think, later on, maybe in HL, but just for now, it's important that we assign an actual mathematical number to these bond orders. Now, there are trends in strength that go along with bond order. As you can probably imagine, a triple bond is stronger than a double bond, which is stronger than a single bond. And what stronger means is that it would require more energy input to break apart those atoms, to break apart those bonds. So it requires more energy in general to break apart a triple bond than a double bond than a single bond. Okay, pretty easy. Now, the trend in bond length is actually the opposite of that. Hopefully you can picture that. As we get stronger and stronger, our atoms get held tighter and tighter together, and the distance between their nuclei actually decreases. So single bonds are the longest, doubles in the middle, and triple bonds are the shortest. So that's the opposite trend of strength. If you can just remember that, I think it should be easy to remember that bond order means, or higher bond order means stronger bond, and then length is the opposite trend of that. All right, so let's see some real examples. CC triple bond is 839 kilojoule per mole at 298 Kelvin. Its length is only 120 picometers. C double bond C is less than that in terms of strength, 614. Its length is a little bit longer, 134. And C single bonds, 346 kilojoule per mole, bond length 154. So you can see that going from a single bond to a double bond does not actually double the bond strength or the enthalpy, the energy required to break it. It's a little under half, and a triple is a little under triple the single bond enthalpy, right? And of course, the bond length also does not half or 1/3 itself as we go from single to triple. And I think the main reason for this is that a double bond and a triple bond, the bonds within them are not exactly the same. There's sort of one strong one, and the others are weaker that sort of come above and below the main single bond. And we will learn about that later in HL, I think. All right, that's all for bond order, so keep those in mind. We'll move on to 2.2.3, coordinate bonding. This is just a special definition and type of covalent bond. So, coordinate covalent bond, sometimes called a dative bond or dative bond, although I think that's an older name that we don't use so much anymore, so stick with coordinate bond. A coordinate covalent or dative bond is a covalent bond that forms when both electrons come from the same atom. Okay. So up until now, we've basically drawn Lewis structures where most of the covalent bonds come from each atom sharing an electron that come together to form a pair. One electron from each atom to make that pair. But a coordinate bond is where both electrons come from one atom initially, and they sort of donate into an empty space on another atom. So you can see that here we have electron donor. It's got a full octet. It's going to donate a pair into an empty space on an electron acceptor atom. Now when they're done, it looks the same as a lot of other molecules we've seen. It looks like Cl2 or F2. They both have complete octets through sharing one pair in the middle. But these coordinate bonds were formed with both electrons coming from one atom. So we've actually seen, I think, an example of this in my previous videos. The molecule or polyatomic ion NH4+ is usually made this way through coordinate bonding, where the nitrogen donates a lone pair that it owns into an empty s orbital on an H+, a hydrogen that's lost its electron. So maybe we can play this video. Let's see. NH3 donates its pair into H+, and in the end, that positive charge still needs to be accounted for. So now it's on the new molecule here, the new polyatomic ion, NH4+. One more time, it starts as NH3 with no charge. H+ comes in, pair gets shared, covalent bond is formed, and we get NH4+. So a lot of bonds are actually made this way, and I'll try to point them out when we see them in the future. Now, a lot of transition elements, transition metals. These will be metal centers that have lost some electrons. They're cations. Things like cobalt 3+ or iron 2+ on my slide here. These are metal centers. These often have such empty spaces that can accept electron pairs from donors. So things like NH3 we just saw has a lone pair that it can donate. Things like Cn- also have a lone pair that they can donate, and that one's even negatively charged, so it can do an even better job. These can donate into empty spaces on metal centers. HL students will see this a lot more in the future, but just for SL you should be aware that these exist, and they often have 6 partners or 6 things donating to them to form this kind of weird octahedral cube shape. So when coordinate bonded groups do this, the Cn- or the NH3 here, they get a special name. They're called ligands. Ligands in a coordination complex. This whole picture here, either of cobalt or iron, is a coordination complex, and the things attached are the ligands. So ligands always have a lone pair of electrons to donate to the metal center. This is a definition that they must follow. Can't be a ligand without donating an electron pair, a lone pair. But I think that's really as far as we're going to go for now into coordination metal complexes. Yep, so that brings us to the end of 2.2.3, and we'll start 2.2.4, hugely important and much longer, well, a fair bit longer section here. So we're really going to get into 3D geometry of molecules and ions here. So this section is called the valence shell electron pair repulsion model or theory. This is shortened to VSEPR, which people often just say as VSEPR. VSEPR theory, VSEPR modeling, valence shell electron pair repulsion. Alright, so try to remember the acronym and the full name. I haven't seen that appear on paper 1 or something for IB exams, but I could definitely see that being a question. What does the acronym stand for? But you can sort of tell from the name what it's going to try to describe. It's going to try to describe 3D structures with the idea that electrons and electron pairs try to get as far away from each other as possible because they repel each other. And that will ultimately determine the 3D structures that the molecules and ions form. So VSEPR theory. VSEPR theory is a model to explain 3D structures of atoms and molecules. It assumes some things. First, electron pairs repel each other and therefore arrange themselves as far away as possible from each other. Non-bonding pairs, or lone pairs as we know them, occupy more space than bonding pairs. Okay, so things that are equal, like two non-bonding pairs, two lone pairs, or two bonds, or two double bonds, or something like that, generally can exert the same pressure against each other in terms of these spacings and angles. But lone pairs actually occupy more space and can sort of exert more force on things around them. Double and triple bonds occupy more space than single, but less than lone pairs. So there's the next part of important information. So double bonds, you can imagine, contain more electrons, more density, more negative repelling force, so they could repel single bonds nearby, shared pairs, further away from themselves. But as it mentions here, they don't possess as much repelling power as lone pairs. Lone pairs are kind of the king of taking up space and repelling things around them. So following these ideas, we should be able to build some common geometries and predict the 3D shapes of many molecules and ions that we've discussed already. So we do also have to get into how do we express molecules and ions on a two-dimensional page or screen. So we've seen Lewis dot diagrams, that's one way, but they really don't take into account 3D structures that well or that often. So there's other things we can do. In organic chemistry, we really use the skeletal structure here on the left. I'll briefly explain how this works. You've probably seen this a lot in various papers or documents or videos. Skeletal structure is a very quick and efficient way to draw organic molecules that contain a lot of carbons. But it does require the reader or the student to understand some rules about how to read this kind of structure. So the first rule is carbon atoms will be shown as corners on chains in the skeletal structure. So anytime you have a line change direction and there's like a little vertex or a corner there, that really represents a carbon atom. So I can just draw them in here to show you. So all these little corners represent carbon atoms, wherever the chain kind of changes direction. Alright, then you can see other atoms are generally labeled as themselves. We've got nitrogen on the top and bottom right. We've got an oxygen on the left. We've got a couple of hydrogens also labeled. But a lot of hydrogens in these structures are actually not explicitly labeled. Alright, so we know that carbon usually forms 4 bonds, right? In 99% of cases. So the way that we understand the skeletal structure is that any place where carbon does not have 4 bonds, the other bonds are containing hydrogen atoms. So for example, here on this one, that carbon only has 2 bonds, so we must understand there are also 2 hydrogens attached to this carbon. Same for this one on the left of it. It only had 2 bonds, so there must be 2 hydrogens attached. We have to just understand that by looking at this structure. What about other carbons? Well, most of them have 3 bonds in the rest of this structure. You can see there's some double bonds and single bonds here. So this carbon only having 3 must have another hydrogen. Same here. We have to understand these have extra hydrogens attached to make sure that they have 4 bonds. Okay. A couple of the carbons in this ring structure already have 4 bonds, like in the top left with the OH group, or the bottom right with the N. But this one also on the right must also have a hydrogen to have 4 bonds. So it's really important to be able to identify where there are actually extra hydrogens attached. Okay, let me clear this up. I think those are basically the rules for understanding skeletal structures. Then I have a space-filling structure on the right, the exact same molecule, serotonin as an example. So it has really similar shapes and angles and even 3D geometry. But the space filling also sort of shows the relative size of the atomic radii inside the molecule. And sometimes it's better to look at just to get a general idea of the spacing and electron density regions of where electrons will mostly exist in this molecule. So both of these are commonly used. Probably skeletal structure is used by organic chemists. Space filling is used by computational or other types of chemists. But we sort of all need to learn how to use and understand all the forms. Okay, moving on. So, VSEPR electron domains. This is an absolutely key thing to understand about VSEPR theory. What is an electron domain? An electron domain is described as a region where one or more pairs of electrons can exist in a molecule. So, for example, an electron domain can be a lone pair. I have one of those circled at the bottom of my diagram here. Right here. What else? An electron domain can be a single bond. That would be like my one black line on the right there. Or a double or triple bond. I've got one of those on the top here. Single bond on the right. So those are regions where electron pairs can exist, right? But it's important to note that each of these is only one electron domain. Okay? A lone pair is one domain, a single bond is one domain, a double bond, even though it has two pairs, still exists essentially in the same location, so they are one domain, and the same would be true for a triple bond, that's one domain. So the example I gave here was the nitrate anion. It has sort of one of each of these types at least, and then there's a bunch more lone pairs on the oxygen. There's another single bond as well. Okay, so absolutely know these definitions. Now let's get into the geometries. And these are often modeled with the idea of balloons that are attached together at their sort of knots that are tied. I think that's generally a good representation of this. You can imagine if you blow up two balloons and you tie them together very tightly at the knots, they're not going to be at some angle to each other, right? Just two balloons tied together, they're going to try to separate as much as possible, and essentially the centers of those balloons will be completely opposite each other in space. We know that as a 180-degree angle. A little bit of mathematics coming into this, but we have the straight line here, right? It's a 180-degree angle. A full circle is 360, right? So this is a half circle between the centers of these balloons. And you can see that represented in kind of an atom on the right here. If it's got two electrons that's able to bond, maybe something like beryllium, we've drawn the Lewis structure before. When those electrons form domains by sharing with an incoming hydrogen or chlorine or something, we will get two domains, and this will be a 180-degree angle between those bonds. This geometry is known as linear. It's like a straight line, right? Just goes straight across 180 degrees between points. So simple, pretty simple geometry. What else? What happens if we have three domains then? Imagine tying three balloons together at their knots. They're going to try to separate from each other as much as possible and not overlap because those gases are pushing on the balloon skins, right? So we get this kind of triangle shape. This has 120 degrees or 1/3 of a circle, 1/3 of 360, in between the center of each balloon, which represents our bonding. So we had these three axes, right? We got 120 between each of these. And that will generate a geometry like what's shown on the right side here with boron. Boron has 3 valence electrons. It's going to arrange itself in this way most of the time. When it makes 3 bonds, maybe hydrogens or fluorines or chlorines or whatever come in here and share, they're going to separate 120 degrees from each other. So this geometry is known as trigonal planar. Trigonal planar. Trigonal kind of sounds like triangle. Planar is like plane. Mathematical definition of plane is a flat surface. So triangular flat surface, that's what you should think about, and you absolutely need to memorize this name, trigonal planar, for 3 electron domains. Okay, good. Next, what happens if we have 4 domains, something like a carbon? Now you can imagine blowing up 4 balloons and tying them together, and suddenly it becomes a 3-dimensional structure. The first 2 that we looked at, well, the first one's essentially 1-dimensional line. Second one is 2-dimensional trigonal planar. They're kind of flat on a surface. But here we have a 3D structure. These are able to separate from each other by going into 3 dimensions. And the angle between one balloon and each of the other 3 is 109.5. That's just the way it works. So we've got all our different axes here. It's 3 dimensions now, so it's very hard to draw. But the angle between any 2 of these is 109.5 degrees. 109.5, 109.5, 109.5. There'd also be between here, 109.5, and between here, 109.5. Very hard to draw on a 2D screen. But between any pair of balloons, there is a 109.5 angle. And you notice that adding 4 of those together no longer equals 360. We're into spherical mode now instead of circular mode. So 109.5 is possible. And that generates this kind of tetrahedron 3D structure on the right here. If you could consider all the bonds that would come around a center, carbon will often form 4 bonds here. And so it will have this 3D tetrahedral structure. 109.5 angle between each of the bonds. Alright, so keep that in mind. Memorize that name, tetrahedral, for 4 electron domains. So we can put these in a table with some examples then and some labeling systems. So if we have 2 domains, we have linear electron domain geometry. We also have something called linear molecular geometry. That's something I'm going to introduce on the following slide. But for now, we're just considering where the molecular geometry is the same as the electron domain. So bond angle 180 degrees. We can label this with an AB system as well. So AB2 means you have a central atom A. It has 2 domains attached. B2, these are bonding domains. That's what B stands for. So some examples of this would be CO2, carbon dioxide, beryllium chloride, BeCl2. If we have 3 domains, we have trigonal planar, bond angle 120. The label for that is AB3, 1 central atom A, and 3 bonding domains, B3. Examples of this, boron trifluoride, BF3, or nitrate, NO3- polyatomic ion. If we have 4, tetrahedral geometry, 109.5 bond angle, label AB4, central atom A, 4 bonding domains, B4. Examples, CH4, that's methane, NH4 plus, ammonium, polyatomic ion. Alright, so nice summary there. Now, let's talk about what happens when there are lone pairs on the central atom. This is where some differences can happen between what's called the molecular geometry and the electron domain geometry that we just discussed. So lone pairs, generally, we don't observe them as a part of the shape, a part of the geometry of the molecule. They're just holding some electrons. There's no bonding, but they can affect, as we said, bonds around them, push them away from the negative charge density on the lone pair. So what if we have a trigonal planar geometry electron domain, but in one of those domains we have a lone pair instead of a bonding pair? That's going to give us an AB2E label. We label the lone pairs with E. I don't really know why. I guess E for electron. But that lone pair E is going to push the other bonding domains away from it and towards each other. And that's going to lower the bond angle that we observe in that molecule or compound. So examples like SO2, sulfur dioxide, or NO2 minus, nitrite, polyatomic ion. You can see a little 3D structure of this I've drawn in the top right. So this is something like SO2 or NO2 minus. You might think that looks like they have two domains so that they would be linear, but if you actually draw the Lewis structure and count the electrons, the central atom S or N in those has a lone pair attached in one of the domains. It's going to push the bonds closer together. So whereas they might normally be 120 in regular trigonal planar, they're going to be less than that, maybe 117, 115, around there. And instead of trigonal planar, now it's not really a triangle shape as it was before, but it's a bent shape or V shape. Upside down V in my little diagram here. You can kind of see that. That shape bent or V-shaped. Specifically the 120 variant of a bent molecule. It's around 120 degrees, but less than that due to the lone pair. Okay. So trigonal planar electron domain geometry, the molecular geometry can be the same as the electron domain, or it can be bent if one of the domains has a lone pair. Let's go tetrahedral then. So the regular tetrahedral geometry has 109.5, that would be AB4. What if, though, we replace a bonding pair with a lone pair in something like NH3 or H3O plus polyatomic ion? In those central atoms, they have a lone pair as a electron domain. That means they're going to have AB3E label. One of those bonding pairs changes to E, and that non-bonding pair, E, pushes away the bonds from it. So our bond angle in this ends up being less than normal, less than 109.5. And you can see that on my slide here in the middle, it's maybe about 107.3. So that's AB3E. That also has a special name that you must remember here. Trigonal, pyramidal, or pyramidal, depending on your pronunciation. So it's trigonal again. It's like a triangle with three things attached. But it is no longer planar. It forms more of a pyramid shape, three-dimensional shape. Trigonal pyramidal. Definitely something you have to remember. So memorize that. It's AB3E, one lone pair on a tetrahedral electron domain geometry. Next, tetrahedral. What if we have two non-bonding pairs? Well, this is going to be AB2E2, something like H2O, water, very common, or NH2 minus. It's like ammonia that's lost a hydrogen or an H plus. So this is also going to create a bent molecule, but the two lone pairs are going to push the bonding pairs even closer than any of the previous examples. two of them now push the bonding pairs much closer together, so it's much less than the usual 109.5 bond angle. So this is also bent, but we can label it with bent 109.5 version, or V-shaped 109.5 angle. Okay, so definitely memorize these labels, angles, electron domain geometry, and molecular geometry. Now, do I have some video maybe to help show the 3D structures of these? Yes, so we'll start with bent trigonal planar version, something like SO2. Generally looks like this. The lone pair would be on the third domain of this, so on the opposite side of where this is the V-shaped structure. Okay, interesting. What about trigonal pyramidal, something like ammonia, NH3? The lone pair would be on the top here, just pushing everything else away from it. Less than 109.5 angle. All right, and then V-shaped or bent 109.5 version. You can see water here. A lot of you have probably seen this before. So there'd be two lone pairs on the opposite side of this V-shape that are pushing them together. Okay, hopefully you got that. If you need to review again, watch what I just said again. Let's move on. So just some points I forgot to mention. Including the lone pairs in the geometry leads to differences between the electron domain geometry and the molecular geometry. So sometimes they are the same, but if your central atom has lone pairs, your molecular geometry will not be the same as the electron domain geometry. So one more time, let's look at tetrahedral. This is often the most difficult to comprehend, most complex, most variability in this. So here's a methane CH4. Let's just look at this from various angles as we turn it around. There's a 109.5 angle between each of these white balls, each of the bond lines. Very much a three-dimensional structure that it's difficult to draw on a 2D page. Alright, so then we can have a bit of practice here. Can we label the electron domain geometry and molecular geometry of various centers on serotonin? The first example I gave today of a complex molecule. Let's see if we can. So this nitrogen. One more thing I forgot to mention about this skeletal structure and the space-filling structure is that lone pairs are often not explicitly drawn with the Lewis dots, right? We have to understand where they exist or where they don't exist. So this nitrogen is not charged. It has 3 bonds, but that means it has its usual lone pair. 3 bonds, 5 valence electrons. It needs to have 2 electrons in a lone pair here. So that means its electron domain geometry is tetrahedral. Okay, is its molecular geometry the same? Well, as I said, when there's a lone pair, not the same. So what is it instead? It's missing that one space where the lone pair is occupying. So this is trigonal pyramidal. IB-SciGuy. You can check on my previous slides. Alright, the hydrogens we don't really need to label. They're not centers of a complex bonding position. But what about this one? This corner is a carbon, right? C. So how many bonding or non-bonding pairs does it have? Carbon will usually form 4 bonds, and it does indeed here form 2 extra hydrogens, then one with CN, one CC on the left. So I'm just going to write E for electron domain is tetrahedral. And M for molecular geometry is also tetrahedral. No lone pairs affect this. So they are the same. This one is essentially the same. 2 hydrogens and then 2 CC bonds. So I'm just going to go a little bit quick. E is tetrahedral. M is tetrahedral. What else can we look at? What about the next carbon in this chain here? This does not have any hydrogens attached, but it has a single bond going up, single bond going down left, and a double bond going down right. That's 3 domains. That means this electron domain geometry is trigonoplanar. Okay, that means this electron domain geometry is trigonoplanar. And the molecular geometry is the same. There's no lone pairs on this. What about this carbon? It will be the same. It's got 3 bonding domains, AB3, so it will be the same. What about this nitrogen on the bottom? Does this have any lone pairs? Yes, it does. It's forming 3 bonds, no charge or anything, so it's got a lone pair here. So this nitrogen will be the same as the one that we did first. Tetrahedral electron domain geometry, trigonal pyramidal molecular geometry. Okay, we've got 2 carbons here. They both form 4 bonds, no lone pairs. They're going to be the same as these. We've got more carbons here. 1, 2, 3, 4. If you count carefully and count all the hydrogens that are attached, they have 4 bonds, no lone pairs. So we can group essentially all of these as the same label. Trigonoplanar geometry. AB3. Alright, what's left? There's an oxygen here on the left. Does this have any lone pairs? Oh yes, so it's forming 2 bonds as usual. That means it has 2 lone pairs. So this is going to be something E2, right? It's got 2 bonding domains as well. So that's AB2E2. The label for that is electron domain geometry tetrahedral, 4 total. And molecular geometry V shape less than 109.5 angle version. Alright, that's basically everything labeled in this. Sorry it got quite messy, but you can do this practice yourself. Just go find a skeletal structure. There's millions out there. Try to label what each atom is in terms of its electron domain geometry and its molecular geometry. You can ask me in the comments or ask like ChatGPT or your teacher or someone to confirm. Alright, so I just want to make a note about structure notation now that we know these geometries. For tetrahedral structures, we often use wedge lines and dash lines to show how 2 of the attached atoms are in different planes. So what do I mean by that? So a wedge line is going to look like this, kind of a long triangular section that's colored in, usually black. And a dashed line is not exactly just a dotted line, but it's going to have the same shape as the wedge line, just dashed. So it's going to usually look like this, the same kind of triangular shape, but instead of being completely filled in, it has spaces in it. And this represents two different directions in 3D space, okay? So a wedge indicates a bond that is in front of the defining plane. So it's coming out of the paper towards you or coming out of the screen towards you. The dashed line indicates a bond that's behind the defining plane. So that's going into your paper, or behind your paper, or behind your screen. And a regular, just black line indicates that the bond is in the defining plane. So it's like on the plane of the screen or the paper. So a tetrahedral molecule is going to usually have two that are in the same plane. So two bonds that are just drawn with black lines. And then one behind the plane and one in front of the plane. So we can see here, maybe this is ammonia or something. Oh, sorry, methane. CH4. I've got the red and the blue hydrogens in the same plane. And then I've got the orange hydrogen behind the defining plane, going behind the screen. And I've got the black wedge line attached to the green hydrogen coming towards me out of the screen. Okay, now I often forget whether dashed or wedge means going into or coming out of the screen, but it actually very rarely matters, okay? The important thing is that if you have a wedge and then a dash, they are going in opposite directions. It doesn't usually matter whether you know that one is coming out or into the page, just that you have two going in opposite directions. You can label them whatever. Usually. Okay. Pair repulsions then. As I mentioned, lone pairs are highly dense regions of negative charge density. They provide strong repulsion to any bonds around them. This widens adjacent bond angles and shrinks bond angles across from them. Think about scissors, right? You've got your lone pairs applying this kind of pressure. It pushes the scissor blades closer together and lowers the angle between them. So in terms of repulsion, lone pair to lone pair will offer the greatest repulsive forces and angle separation. Lone pair to bonding pair offers quite a bit of force, but bonding pair to bonding pair is sort of the weakest repelling force. And that's summarized again in the tables of molecular geometries here. So V-shaped can be less than 120, trigonal pyramidal is less than 109.5, and bent V-shaped tetrahedral version is much less than 109.5 angle. Alright, and finally, as I mentioned, double bonds and triple bonds contain more electron density and repulsion than single bonds. So if you have double bonds near single bonds, the angle between the double bond and single bond will be larger, usually. But the angle then between single bonds alone needs to become less than normal. I have a good example of ethene here, C2H4. You can see this would normally be trigonal planar with 120 angle. But the double bond in the middle pushes everything away from it, giving a slightly larger angle, 121.5. And that's going to push the single bonds at the ends of this molecule. There's two CH bonds. They're just single bond domains. They can be pushed closer together by the double bond in the center of this molecule. Just in case that's not clear, the actual Lewis structure for this that we might draw. The actual Lewis structure that we might draw for that is something like this. Ethene. So this double bond pushes strongly away the other pairs. That makes that angle larger. And that means this angle inside goes less than 120. 117 in this case. I'll play the video again. So smaller angles on the ends between CH bonds, larger angles in the middle between CC double bond and CH single bond. So kind of that scissor action happening. So 3D Lewis structures. Can you draw them for ammonia NH3, dichloroethane C2H4Cl2, or propene H3CCHCH2? Give it a shot. If you want to see my answers, I'll move on now. So NH3, you can draw the normal kind of Lewis structure start. There'll be a single bond with H. But before I go and draw the next two, I have to realize I want to draw this as a 3D Lewis structure now. And if I'm going to have a defining plane, usually it's a good idea to include your lone pair in the defining plane. So I'll just show a dotted line here to show my two things that are in the same plane. Just for clarity, I'll redraw this now that we understand this. So that means my next hydrogen needs to either be a dashed or a wedge line. So I'll do dashed and then wedge. This is a good representation of the 3D structure of NH3 ammonia. We've got lone pair and a hydrogen in the same plane, and then a hydrogen going into the page and a hydrogen coming out of the page. Alright, what else? C2H4Cl2. So normally, we can draw this like this, right? It doesn't really matter where we put these two chlorines, it's not clearly defined. But now we know that these carbons are not flat on the page, they are tetrahedral, they've got 4 bonds, AB4. So we need a better way to represent this. First, we'll draw the things that are in our defining plane of the screen or the page here. So CC bond, we'll make that in the plane, and then we can do one more on each carbon in the same plane. These are flat on the screen. And then I want to show dash lines with these hydrogens on each side. So these are either coming into the page or going out. And then wedge lines for the last ones that will contain my chlorines. Okay, so that is a decent 3D structure for C2H4Cl2. But you might ask, why'd you put the chlorines there? Why didn't you put the chlorines on the same carbon? Totally decent questions or understandable questions. And yeah, I could have put these H's and Cl's at any position, basically. I could put a chlorine here, and then an H on the other side. I can put an H here. I can put a chlorine here on the other side. Doesn't matter. Oops. Let me erase that. Put a chlorine here, and that means my last one remaining will be hydrogens. Okay, so if that chemical formula, C2H4, is all I have, there's no telling which way that you should draw it, really. You just need to have all the atoms in there, and you need each carbon to have 2 bonds in the same plane, and then 1 bond going out of the page, 1 going into the page. That's really the only requirement. Okay. So that's here done, here done. Last one then, propene. So this contains a carbon-carbon double bond. It must, if you count the atoms and try to draw the structure. CH3 and CH2. So this left carbon must be trigonoplanar geometry, both molecular and electron domain. So that doesn't have a 3D structure. Trigonoplanar things, we don't need wedge or dash lines. They're flat on the page. It's the only way to really draw them. Now this carbon in the middle is also trigonoplanar. It has a hydrogen here, so 3 domains AB3. No need to draw any 3D structure. But this one on the right, this contains the CH3 group that's actually on the left of this formula. So I'm going to draw 1 hydrogen in the plane, 1 hydrogen going behind, and 1 coming towards me, dash and wedge lines. This one is tetrahedral, AB4. So it's the tetrahedral centers that are going to have the 3D structures. So one more time, just clearly, I'll draw it again. Wedge line here, finish up. Propene. 2 trigonoplanars. Whenever you have a double bond, you're going to have those trigonoplanar carbons. And then 1 tetrahedral on the right side. So, sorry, this is the answer for the third one here. Alright, maybe that's a good place to stop. Okay, I do have some practice questions here. A, B, C, D, E, F, G, H, but this video is already long, so I think I'll make them a separate practice video the same way I did for Lewis structures. If you're interested in that practice, check out my next video coming soon. Then that's all for today. Thanks for listening, guys. Good luck learning the molecular geometries and VSEPR theory, and I'll see you in the next one. Thanks.